Howdy! So today I'm going to show you guys how to do second order circuits. Yeah, I know, it's that time of the semester where you're like, what is that? Well, allow me to demonstrate. So, here's an example. It looks pretty easy and nice and innocent, but trust me, it is. Okay, so basically the first and most important thing about second order circuits that you need to know is you need to know the initial conditions. And based on what you're doing the circuit over, which for me I'm doing it over the current, which is going to end up in a differential equation like this, di naught squared over dt squared, and da 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 da. That's how you establish which type of initial conditions you want to use. Okay, first things first, let's find I naught of 0 plus. Alright, at 0 plus, and notice that there's a switch here, and that means it closes at t equals 0. So this tells you that the circuit has been open for a long time, okay? For a long time. So that means this is going to be an open source, and this is going to be a short. Alright, let's do this. At time equals 0 minus, this is how the circuit looks. So basically, we can solve for VC of 0 minus as well. You know what? Let's do that too. Okay, VS and R are in series, right? So obviously you want to find the current going through them, but notice that there's no current going through here. The current equals 0 because of this short circuit. Well, yeah, because of this short, and there's an open source here. So the voltage drop is going to be 0 because there's no current, right? So Vs is equal to Vc of 0 minus, right? And we know that Vc of 0 minus is equal to Vc of 0 plus because a capacitor's voltage doesn't change instantaneously after you close, after time t equals 0 plus, right? Right. Alright, so we want I naught of 0, and I naught of 0 is going this way. We can establish that I naught of 0 minus is equal to 0 because there's no current going through the circuit at all, right? So, and I naught of 0 minus is equal to I naught of 0 plus because inductor current doesn't change instantaneously, right? Right. So we establish these two things. Vc of 0 plus is 12 volts. I naught of 0 plus is 0 amps. Good, good. Alright. Next thing we need to do is solve for di naught of dt of 0 plus. I know what you're thinking. You're going to try to do something like this. Find the derivative of this and that, and you're going to get 0. Well, that's not right. I'm sorry. It's not right. I tried that too. I wish life was that easy. Okay, the trick here is to redraw the circuit, right? Redraw the circuit, at 0 plus. This is the circuit at 0 plus. So you can have VC of 0 plus here, V naught of 0 plus, dot, all this, and that's closed. We know two things about this. We know the voltage here. We found it in this part. Okay, so we know the voltage here, and that gives us the voltage here. We know the current going through here is 0. So, how the heck are we going to solve for this thing? Well, that's easy enough. First, we know that the current going through a capacitor is equal to C dV over dt. But we don't want dV over dt. What do we need dV over dt for? I don't know. Whatever. Alright. And we know that the voltage in an inductor is L di over dt. Whoa, there's a di over dt there. Let's use that, right? That's what we're looking for. Di naught plus of dt. Okay. So we're just gonna switch all these things. Let's call this Vc of 0 plus. And here, Vc of 0 plus is equal to Vc of V naught, right? Vc of 0 plus, because they're in parallel, they have the same voltage. blah, blah, blah. Okay, so we can just say di over dt of 0 plus is equal to v naught of 0 plus over L, right? If you isolate di over dt, that's the equation you get, and we end up with an answer of 240 amps per second. Not bad. So we've solved for our two initial conditions. Now we want to solve for A, B, and C, right? So basically, now is the time where you actually do the circuit. This circuit. So what I'm gonna do, you can pick your poison, you know. You can always solve this circuit many different ways. But I did node voltage. Let's call this VC of T. And you know VC of T is equal to V naught of T, right? Actually, let's just change this to V naught of T, you know, for peaceful purposes. Okay. So, node voltage, right? Let's just do all the currents coming out of this, right? And of course, you gotta change the capacitor and the inductor into Laplacian notation to make it easier for you, just so you can treat them like resistors. So a capacitor turns into 1 over SC. An inductor turns into SL, right? And then you just treat them like purely resistors. Okay. So you do V naught minus Vs over R, right? And that's gonna be your first equation. V naught divided by 1 over SC, that's just going to be V naught times SC. That's your second current. You're going to add all these up because you want all of these to equal to 0. So V naught over SL is going to be your third current. So you put all these in this formula. But I thought we were solving for this current, right? I thought we were solving for the current going through here. What's going on? This doesn't look like it. Well, that's why I have this little trick over here, this little friend of mine, right? V naught of T over SL is equal to the current, right? Obviously, like, come on, that was easy. So V naught of T is equal to I naught of T times SL. So everywhere you put a V naught, just plug this in, and then we're gonna end up with the equation that involves I. So you do all that, and this is what you end up with, right? You plug in I naught here, I naught SL, you get I naught SL over R plus I naught T S squared LC, and you get VS over R. Fine, whatever, right? Okay, whatever. So now what do we do? First things first, you need to make sure that everything you did has the units to cancel out what's like going against it. Here, let me show you. So this S here, this Laplacian here, just turns into a derivative of whatever is here, right? So this is going to be the derivative of I naught of T times L over R. And then this is going to be the second derivative of I naught of T times LC. And this is just lame. It's boring. And then on the right here, you get VS over R, right? You have to isolate it to the other side, you know. Blah, blah, blah. Okay. So, from this, let me just write it out. From this, you get these. Oh man. You get d squared I naught over dt squared times LC plus di naught, let's do this, over dt times L over R plus I naught of T is equal to Vs over R. This is the equation you end up with. Sorry about my handwriting, it's pretty terrible. So from this you can tell that A is equal to this, right? A right here is equal to that. B is equal to L over R. And then C is equal to VS over R. Wow, that was really easy. You just solved a whole second order circuit. And that's it, guys. That's literally it. Thank you.
Hey everyone, so today we will be learning how to do second order circuits, particularly this kind of big ugly circuit, because this is probably the hardest circuit you will see in your class. So let's get into it. So first things first is we are trying to find voltage across the inductor, and when solving a differential equation, it's helpful to know the initial conditions, such as the initial voltage across the inductor, or whatever component we're trying to find it for, and the derivative with respect to time of that voltage or current over that component, because it makes solving for the constants in your differential equation a lot easier, what you should do. So let's get into it. So voltage, if we know the voltage across capacitor at time t equals 0, then we can solve for the voltage across the inductor at t equals 0, since when it moves, the switch moves to position B, we can, or the voltage across these two components will be equal. So at time t equals 0, we're focused on this part of the circuit, and therefore, and there's no, since it's at position A for a long time, no current through the capacitor, so we can do a simple KVL and just do 50 minus the voltage across resistor 1, R1, voltage source 50 divided by the equivalent resistance, and we get that voltage across the capacitor, which is equal to voltage across the inductor initially, is 20 volts. So the other thing to know is the derivative of the voltage with respect to time at t equals 0. And with a circuit with a current, or just a dependent source in general, it is common and probably easiest to do a Thevenin equivalent circuit. And so what we can do here is take this whole circuit, and our goal is to just kind of transform it into just this simple resistor. So, and you'll see why this helps us solve things out here in a second. So, we have our Thevenin equivalent voltage and current. So, it would be helpful to get these two in terms of each other. So, that is just a simple current divider. So, that would be I phi is equal to minus opposite directions, 150 divided by 150 plus 60, which just simplifies to negative 15 over 21 times IT. And then our Thevenin equivalent voltage is negative 10 I phi plus the voltage across the parallel component or combination of the R3 and R4 times the Thevenin equivalent current. And so we know I phi in terms of IT. We just plug it in, do some number crunching, right? And we get that our Thevenin equivalent resistance is 50 ohms. So why does this help us? Well, now we can say that instead of all that nastiness we had up there, we just have this simple circuit. So when trying to find the derivative, that term comes from the capacitor relationship for current. I is equal to C dV dt. And we know that they're in parallel, so dV dt should be the same for both of them. So dV dt is just equal to I divided by C. So initially, the current through the inductor was 0 because back at the very top, it wasn't connected to anything. So therefore, negative the current through RT is equal to the current through the capacitor, right? Just keeping track of sign convention. And we get that the current through the capacitor is negative 0.4 amps. And then using our relationship up here, we get that the derivative of voltage is negative 50 kilovolts per second. So now onto the differential equation. Since we're trying to find voltage, I simply did a KCL. Whatever you're trying to find, it makes sense to do the opposite. So like finding current, you should do a KVL, finding voltage, KCL. So I said I phi, the sum of these two currents across R3 and R4, I phi plus minus 10 minus V naught, that's what this voltage is here, if I said that this is 0, divided by R3 is equal to, the sum of those two currents is equal to the currents across the inductor, which is V naught over SL, and plus the current through the capacitor, which is CS V naught. And S is just our derivative operator. So we want to get rid of this I phi term, so we can say that I phi is equal to minus 10 I phi minus V naught over R4. Do some simple algebra and get I phi in terms of V naught and R4 and a constant. And so then plugging that back up here, we get this expression. And then from here, we can factor out a V naught from each one of these terms. And since the S is our derivative operator, we don't want it in the denominator of a fraction. We like it to be in the numerator. So therefore, if we multiply everything by CSL, or SL, my bad, we get this expression right here. So this is just a bunch of constants, right? And so if we do some rearranging, then we get, and we plug in our numbers, we get that our differential equation should be 4.1 times 10 to the negative 7 seconds squared, times the second derivative plus 1 times 10 to the negative 3 times the first derivative plus V naught is equal to 0. And this is a differential equation that we can solve. I'm not actually going to do it here. I just wanted to help y'all get to this and solve for the initial conditions in this kind of complex circuit, because at this point this is just solving a differential equation, not actually having to do anything with the circuit. But if you'd like to check your answer, this is it. This is in volts. So we got 20 e to the negative 1250t cosine 938t minus 26.67 e negative 1250t sine 938t. And that's it.
Alright guys, so if you made it this far in the video, major props to you. We went through a fairly simple second order circuit as well as a fairly complex second order circuit problem. And that's about as hard as it's going to get. We have a whole separate video on our channel for solving differential equations, but we wanted to include some final thoughts on finding initial conditions in this video for you. So first, and probably the most important thing that I'm going to mention, is the analog boys theorem. Between a lot of brain power and homework problems solved, we've determined that I don't know is not equal to 0. So basically, if, say, you have a circuit and you don't know the current going through a resistor, that doesn't necessarily mean that there's no current going through the resistor. You still got to sit down and solve the problem. I don't know is not equal to 0. Additionally, we have this complex corollary to the theorem, which states that just because the current or the voltage at time 0 is equal to 0, that does not mean that their derivative is 0. Remember, if nothing is happening right now, that doesn't necessarily mean that there's no change going on in the circuit that could potentially allow there to be a current later. Second, I want to give you this chart right here that's been helpful for me to find initial conditions. Basically, you've got a capacitor here and an inductor here. And then these two columns represent the instantaneous short term and infinite long term. Now we know that capacitors act as open circuits in the long term. However, it's important to remember that in the short term, capacitors can function as short circuits. So think about capacitors have all these electrons loaded up on top of them or whatever, and when a switch closes, instantaneously the capacitor is shooting out electrons just as fast as it can, and it functions almost like a short circuit. And then of course in the long term, capacitors function as an open circuit when they've got the max amount of electrons stored up on top of them. Now for inductors, in the short term, they tend to act more like the open circuit because they have heavy resistance against changing current. So you can think of them as instantaneously, once the switch closes, having an infinite resistance. And then in the long term, of course, that resistance dies down and they function more as a short circuit. These are very helpful sort of ways to think about capacitors, inductors, and inductors in the instantaneous short term and the infinite long term that kind of clear up solving initial conditions. Hopefully you found this video helpful. Please like and subscribe and comment if you have any questions.